Okay. So let's start the second lecture. So the second lecture is the speaker is Hamid Abban, and so he's going to talk about the K-stability and K-moduli of Fano varieties explicit results. Yes.
Good morning. Okay, thank you very much. Thanks for the invitation. It's a great place to be in, and it's a wonderful conference ahead. Yeah, so I prepared a very elementary talk, assuming there are lots of algebraic geometers who are not experts, but there are some super experts in the room. So apologies. So I'm going to talk about various things. The first one is introduction. Introduction, basically, I'm going to say why people care about this, but you have heard this before. It's just for me to wake up. So second part, I talk about some very narrow approach to explicit methods. I'm not going to talk about all of them, especially one based on induction that we did a few years ago with Zichun. So this is a bit old. So it's like a few years ago, right? And then I focus on hypersurfaces and K-moduli. Again, I don't have enough time, so I will be very brief here, but I try to send the main message. So this is kind of recent. And then I talk about one piece of work in K-moduli of Fano threefolds, but I try to give you the picture as much as possible. So this is in the oven. It's still being, maths is finished. We're just tidying up the paper. And it has 8 authors. I was never comfortable with more than 2 in the past. And then it just keeps getting bigger. But this is good. This is a lot of work involved in this. And we're really thankful to those who did the work, and we put our names on it. So these are 4 PhD students or former PhD student, now it's finished, of the person below them. So, yes, so it's substantial work. So hopefully by around this time, and then you should be convinced that these kind of things are just, they involve a lot of work. So first part, why should we care about K-stability? You have heard this before, and I'm sorry about that. So the first one is the Yao-Tian Donaldson conjecture. So basically, you expect that X Fano manifold admits a Taylor-Einstein metric. Which, if and only if X is K polystable. And usually in K-stability talks, no one defines K-stability, or that's the only thing they do. So I'm not going to, I give you some definition in section 2. So at the moment, just come with me, some condition, right? So this used to be a conjecture, and now it's a theorem. So it was resolved by, famously by Donaldson and Son and Chen, Donaldson, Son. But you don't need this. So Fano. Now this is also a theorem. This is in full generality. You can't get better than this, right? So the full generality is just it's a consequence of many results. But the final touch was done by Chen-Yang Xu, Zikon Zhuang, and Yu-Chen Liu. So, but it involves several steps. I'm not going to talk about it. So what, this is a room of algebraic geometers. Who cares? Right? I know. Please edit. Good. So now, so fix n and some number positive rational, then now this is, of course, this is a theorem. This is a theorem. Right. Good. So now then this thing that I'm writing as M KPS, which depends on n and my number nu, is going to parameterize K polystable Fano varieties of dimension n and volume nu, which is minus k x to the. So this is space that parameterizes K polystable objects is a projective variety. And this is something we probably love. Some, one of us at least. Good. So again, this is due to several people, some of them in the room. It gives you compactification, yes. So, so for Fano varieties, there was no theory that would give you a compact moduli space for any Fano. I mean, you could do GIT for those that have GIT, but this is, or some other. So there were ad hoc, except for, so there were ad hoc methods for certain cases, but just assuming Fano, you wouldn't have such thing, but now you do, right? And so I'm going to write it, but I'm not going to talk about it. So I just say. So if you parameterize K semi-stable objects, then you get an Artin stack whose good moduli is this. So it's perfect scenario. So for example, I mean, there are lots of examples, but I'll give you something I like. So if you take P3, that's a Fano threefold, and the moduli is very easy, just point, right? So you could take P3, you can take a line in it, you can blow it up. Again, you get a Fano, but there is again no moduli. You can fix your line. Right? You could take P3, you can take a twisted cubic. You can blow up P3 along this twisted cubic. Again, you can fix your twisted cubic. You get a Fano. And again, this is a singleton. There is no moduli. But you can take P3, a line, and a twisted cubic, and blow up both. Then you get a one-dimensional family of Fano smooth Fano threefolds. Right. In fact, it's much better than that. It's just a A1 family. It's parameterized by A1. So if I wanted to compactify, just add one limit, right? What kind of limits do you have? So you could have a line and that. You could have a line and that. And more. Right. Basically just deform this somehow, right? So if you just want to compactify, just add one of them, right? Gives you, but which one should you do? Which one is the most natural, right? Which one is the canonical choice? So this theory tells you precisely one of these is going to be K polystable, and all others are not. Right? Yes. Excellent question. Thank you very much. I'll come to that in chapter 3, but not for this, but the general picture. But so if I'll tell you now. Yeah, so there's even a bigger project done a few years ago where people studied this Fano threefold, the smooth Fano threefolds and K stability. I'll come to that in a second. But for all the smooth ones, Elena did it last year, I think. So good point. But so you want to add one of these, and later I'll tell you which one. For like 45 minutes, secret is not so bad. You can do it in the meantime. Good, good, good. So I'll quickly move to chapter 2. So instead of starting by definition, I tell you what people used to do. But in the abstract, I said I put my birational hat on, so I'm going to just do birational geometry. So I'm going to start with the pair X and D. You saw some of it in the previous talk. So this is a pair. I'm going to define the log canonical threshold of X and D. And this is going to be the supremum of positive rational numbers lambda, for which the pair X and lambda D is log canonical. And when X is Fano, it comes with minus K for free. So I can define, I can look at the log canonical threshold of X and D, where D is effective and is equivalent to minus Kx. So I'm looking at the set of all log canonical thresholds for anti-canonical divisors. And this is called the alpha invariant. Just like COVID, we have alpha, we have beta, we have delta. We don't have Omicron. So it's not finished. This one. Good. So we have alpha. This is known as the alpha invariant of Tian. And why do I write? Oh, thank you. Yes. Good. Thank you. Yeah. So yes, so you take the infimum. So basically what it does is measuring the singularities of anti-canonical divisors on your X at the same time as measuring singularities of X. Right. So Tian criterion. I write some version of it. It's not the best one and it's not the original. It's somewhere in the middle. So alpha X is bounded below by dimension over 1 plus dimension, implies X is K. But at least you have a feeling of what the relations are. Good. So this is what we had. So some birational geometers were busy getting results on K stability using this until a few years ago when things got better. So I'm going to write some examples of these things. So, oh, it's a shame. The yellow chalk is not as nice as the white one. So continue with white. Example of some of these things. So fix M as large as you like and fix S1 to SNM, obviously depends on M, to be a basis for this vector space. Right. We know what this is, right? So once I've done this, if I look at Si equals 0 as a divisor, so I take one of these and I take the section. I'm cheating. So what by this, I mean, remove the fixed part, right? So take this divisor. So now this is going to be equivalent to minus mkx by design, right? So I divide it by m. So I get this, right? And now I'm going to take right. So this is one of those guys. So if I wanted to compute this number, I would have had to consider this kind of guys too. But in that, I also consider the one I wrote first, just Si equals 0 over m, and many other things, right? So the key thing about m is that I'm taking the entire basis for this. So I'm not omitting anything. So definition. So B is called M basis type if there exists S1 to Sn such that D is like that. Now that is probably the most important definition you see today. Good. So I'm going to do the same thing. I'm going to take the set of log canonical threshold of X and D, but instead of taking D to be any anti-canonical divisor, I take D to be M basis type. So I've restricted myself to this thing. And I take the infimum of this and call this delta M. Now, define delta X with the limit of delta Mx. So a priori, the limit should not exist, but this is a result of Bloom and Johnson. And they tell you what the limit is. If you want me to, I can write it, but don't know if I use it. Hope not. So anyway, so you have this limit, and now there's a theorem / take it as definition, Fujita, and independently by Lee around the same time. X is K stable if and only if delta X is bigger than 1. So basically, so you take this alpha invariant, the way we did it, we used to do it. Instead of taking all anti-canonical divisors, you just take these average type divisors and take the asymptotically. And the asymptotic of this should tell you everything you need about this. Chile, yes, thank you. Yes, yeah. It's important. This is Kento Fujita, not the youngest Fujita that is famous enough, and Chile, yes. So obviously he used more analytic methods, and this was more algebraic. Now, the idea is that, so what did we do? We took all these divisors, and then the idea here is that you can do a lot better by restricting yourself to only these average type divisors, and it's sharp. It gets you everything. So I'm going to do one more step like that. So fix a divisor. What did I use? Divisor E over X. So we saw it earlier. So this is a divisor that may be on your variety, or maybe it may live on some birational model above your variety X. So fix a divisor E over X prime. Say D, which is an M basis type divisor. So it's M and M, sum of SI. So take an M basis type divisor. We say this D is compatible with E if for every J, use this notation, but I don't think I need it. But anyway, so FJME, so it depends on all of this, which is calculated on this vector space. And it is the set of all sections whose order of vanishing along E is controlled by J. It doesn't matter. So I'm going to define a filtration on this vector space that comes from this divisor E, right? Then I say D is compatible with E if, I haven't finished the definition, if for every J, this thing is spanned. Who? D is here. Yeah, okay, no, I know what you mean. I'm not finished. Is spanned by some SIs. Now that's P, right? So the way you do this, really, so you don't start with D. You start with this. You write a basis for this, right? And you write your basis in a way that is compatible with E. So step by step, you maximize your order along E, right? When you write down your basis. Once I've written the basis, you take this divisor D, and then you say this is compatible with that, if you like, right? So the upshot is that D is compatible with E if it has maximum vanishing order along E. Clearly, you just maximize it every time. Right? And now you can do the same thing as before. So delta MX and E is going to be the infimum of log canonical threshold of X and D for D, which are M basis type, and compatible with E. And then define delta X and E to be the limit of delta X. And just as in Bloom-Johnson case, you can prove that this limit exists, and that number is your limit. Position. So proposition says that for any E over X, delta X E is delta X. So it doesn't matter which divisor you fix, where you fix it. If you If you compute this delta, it gives you the same number. Right? So the idea is that basically you go from all anti-canonical divisors to the average ones, and then even amongst them, if you fix a divisor that you like, those that are compatible with it will give you the same number. I can give you the idea of the proof if you have time, if you push me. So, not very complicated. Any questions? So, yes, there is a question. That's my next line. I mean, this as it's written is completely useless, right? So is this, any of this, right? Because here, in order to compute alpha, I have to compute infinite. I mean, it's the infimum of infinitely many divisors. I mean, how do I do this, right? When you restrict yourself to the average ones, it gets better, but there still is infinitely many objects to study. And even if I fix E, I still have infinitely many average divisors to look at, right? So why do I like this? So this provides this induction step. So the idea is that if I have D, right? So D is an M basis type divisor, right? That I want to study. I want to see if my D, so the idea is to start with an M basis type divisor and see if it's log canonical, right? Log canonical, right? Or a multiple of it, right? So I start with D, and because now, if you believe this thing, so I only need to look at those that are compatible with E. So they have maximal vanishing order along E. So because of that, I can write D as something times E plus gamma. So you can write it asymptotically as this, right? And now the pretty part is that, how much do I explain this? So now, the consequence of this computation is that gamma restricted to E is an M basis type divisor. E. Sorry. Yeah, so M prime. Right. Yeah. So and when you write this, people who, I mean, some people in the room know this. So now D is going to be, so if I fix a point, and if I choose E to contain that point or be centered at that point, D is going to be log canonical at that point if and only if gamma is log canonical on E. This is inversion of adjunction. I mean, one of them is adjunction, the other one is inversion, right? So the point being, now this allows me to, so now I fix a point. I'm looking at M basis type divisors concentrated around my point, and I fix a divisor that is centered at my point, and I move to that divisor. I forget my threefold, so or n-fold. I go to an n-1 dimensional thing. So I go one dimension down, and now I look at M basis type divisors on that, and the information I give is similar. So if I have time, I usually write something about Pn, which gives you all the idea, but I don't. So it's not difficult to convince yourself it's true. The next part is, and I'm not going to prove it or say anything. But the idea is basically this induction step gives you everything. Good. So now what it does is, so using this, I'm not telling much here. So using this, one produces a lower bound for delta X. But what I can give you is, for example, if I start with X, I call this Y naught. And then inside it, I take a divisor, I call it Y1. So this is my E, right, in this setup. And then on Y1, I take E, Y2, all the way down to Yn. We have strict divisors. So if I do that, and then for those who like this kind of thing, so if I take the Okonkov body that associates to minus kx, for any divisor I can. So I have an admissible flag and a divisor. So I write the Okonkov body of this. So this is the work of Lazarsfeld and start. If you do this object, so I call it delta y dot minus kx. So this is a subset of n, of course, positive by design. So this is my flag y dot. So I have an admissible flag, and I construct the Okonkov body given by this admissible flag and anti-canonical divisor. And then I let B1 to Bn be the coordinates of the barycenter of this delta y. Then delta x is bounded from below by minimum of 1 over. The point being, if I fix this, if I fix my favorite flag, the rest is something I can compute. I compute these numbers and they give me a lower bound for delta. So if you want to prove X is K semi-stable or stable, sometimes polystable, what you do is you fix your favorite flag, you compute these numbers. It's a hell computing these things. But you do, right? So you have 8 people. So you compute these things, and then they give you some numbers. If they're all bigger than 1, bingo, you're done. If not, you change your flag, try again, right? So that's why this is a good recipe to work with, but each time you use it, you need to know the geometry of your object and choose your flag. And often you run out of flags inside your variety, so you have to take a flag over your variety, and then computations get more clumsy. This changes slightly, but we have formulations for all of this in the paper. So you just follow this recipe and you put your machinery. All you need is this plus a lot of knowledge of geometry of your object, and you get this thing done. So yes, that's how you do this. Any questions so far? Yeah, so as Kosher said, you can't do it in the next few weeks, so in the next few decades, hopefully. Yeah, if you want a description, yes. So the idea is to know which ones, and I'm going to, in the next 25 minutes, I'm going to write something we know, and you see it's still not easy, but in 10 years time, probably it's considered easy. Who knows? So I gave a super shortcut to what K-stability is and what one of the methods that we use is. Now I'm going to talk about some results. So to go to chapter 3. Hypersurfaces. So I'm going to write xd in Pn plus 1. So dimension is n, and this is the degree of the polynomial defining it. And obviously you want it to be Fano. So you have that. So expectation is that all smooth hypersurfaces, Fano hypersurfaces are K polystable. Good. So now, what do we know? So if D is 1, so X is Pn plus 1, then it is polystable. It meets the Keller-Einstein metric, and in fact, is the Fubini-Studi metric. And that's the only case we actually know what the metric is. So, good. For quadrics, again, they're all K polystable. And then if D is n plus 1, they're all K stable. And B is n, they're all K stable. Yeah. Yeah, so I wrote it very badly here. So this is important. Yeah, thank you. Good. So at least we have some expectation that they all should be K polystable, K stable, in fact, except the silly ones. Now, what do we know about the modulus? Right. Okay, there's more. Sorry, I forgot. I'm not writing who did what, but this was probably, I don't know, Euclid or someone. There were some analytic methods, but I think the first algebraic proof was in that paper. So we proved this and that, and we gave new proofs for more or less anything that was known using this method. But this was first by Fujita. And then what is new that is a little bit mysterious is this. Well, again, this is different paper. So yes, so we have this. If D and N satisfy this bizarre inequality, we have it. The point was that we didn't know any examples between these, except some special cases I talked about. So that gives you infinitely many examples in every index. But beyond this is a gap. Oh, yes, K stable. I mean, K polystability is only here, right? Because automorphism is finite there. So. Good. Okay, I'm cheating. I didn't take half of the things. So let's do more. So if X is general, then again, it's okay, we know. But this is not complicated because as soon as you have one example, you know that K stability is open property. So you just write down one, it's K stable, then it follows. But you don't know which general. So also X3 in P4, 5. That's the only one that's not here. Oh, so so basically everything I talked about here, you can write equivariantly, right? And then so if you have more symmetries, easier to check. So you write Fermat with lots of symmetries. So how about K-moduli of this? So how do you compactify? So I'll tell you what is known. Known before that. So So obviously there's no moduli here. So if you take X3 in P3 or P4 or P5, then K moduli is the same as GIT moduli. And hopefully there's only one message at the end of my talk, and it's about this. So this is Odaka Spati-son, this is Xu and Liu, and this is Liu, right? But the way you do it is you take your object and you take a hypothetical limit of this, and you just want to prove that your limit lives in the same space, right? So you use Liu's inequality plus ODP gap conjecture, and it kind of nicely gives you the result. The problem is that ODP gap conjecture is not known in higher dimension. That's why you stop here. Otherwise, the rest is just follows. So conjecture that this should be true for any this for n bigger than what is this 5. Right. So there's some the difficulties you have to overcome, but this should be true. But other than that, we kind of disable. So, for example, so I'm going to take X4 in P4, and I'm going to extend this space very quickly. So I'm going to write it as y0, y1 is f of x4. Tell you what these things are in a second. by1 is g2 of x, and cy0 plus dy1 is h2 of x. So I take this complete intersection inside P1, 5 and 2, 2. So this is x, these are y. So y has degree 2. Y has degree 2, and I have two equations of degree 2, and that's the degree 2 quadric I write here, is equal to x4. So this is the degree with respect to x variables. Good. Now, good. So now take that thing, and in it, I can look at this matrix. I write it here. So matrix A0, A1, A, B, C, D. Thank you. So obviously, A, B, C, D parameters. So now I look at the rank of A. If the rank is 2, then I recover a quartic. What it means is I can just eliminate y0 and y1. They're just doing nothing here, right? And I'm going to take F, G, H general. So I get a quadric smooth if they're general enough. And if the rank is 1, I get a hyperelliptic smooth. And if the rank is 0, I get singular, but for those who like these kind of things, quasi smooth something, right? X224 in P1522. So now these guys, by that result above, are all K stable. These are so they're cyclic covers, and it's easy to show that K stable. There are many proofs for this, and they both appear in Mori-Mukai classification of Fano threefolds. Iskowski Mori-Mukai. Now these are not smooth, but they're clearly deformations of quartic. So they are in the limit. And the theorem we have is that this X222 1522 was smooth or polystable. K polystable. All right. They're all K polystable, and moreover, it's better than that. And if you look at the 224, if you look at the closure of this locus inside MKPS 34, contains only elements of this type. So basically, if I want to compactify quartics, I have to consider these guys too. And if I take a closure of these guys inside my compactification, I still have to take these guys, right? So the picture is complicated. The idea is that the moduli should be 45 dimensional. In it, you have a 44 dimensional. These are the hyperelliptics. And then somewhere here, you have this X224, but this one is closed, right? And this is 42 dimensional. Beyond this, we know a few examples. So I'm going to move to the next part, but I'll come back to this probably. Yeah, so the point is, for hypersurfaces that are not quartic, that are not cubic, we don't even have an expectation of what the K-moduli should be yet. At some point we will.
But if it's stable, you know, similar.
So okay, that's the first result. Is that they have to be KLT. So the Q-Gorenstein KLT. No, you can hit more or less anything, depending on how crazy your object is. But I mean, it depends on the case. Like where you have the GIT for cubics is the same. I mean, you know what they are, right? So they're specified in the analysis of GIT. So they're not that bad. Yeah, I don't know what to do with these boards. I'm not that tall. Not that short. Yeah, so you should be able to recover it from some blow up of GIT. And so the first part, yes. And I mean, this, yes. This is the K1 blow up, yes. That I still don't know. Yeah, so if someone is super brave to do GIT of quartics, we can talk. Good. I'm now going to move to the next one, which I've already started. Oh, I'll keep it short, I promise. So smooth Fano threefolds. Now, what's the study? So as everyone knows, Iskovsky-Mori-Mukai gives you 105 deformation families. So there are exactly that many Fanos. And then step one, decide which ones contain K-stable objects, which ones don't, right? If they do, then a general one should be K-stable by generality property, by openness property. So step one, this is the work of Araujo et al. This is got 9 or more authors. So 87 families contain K polystable objects. And importantly, others don't. So by openness, you have 87 families to compactify. Step 2, prove in each of 87 that all smooth elements are K polystable, or decide which elements are. So this is an ongoing project. Vanya Cheltsov has a secret webpage, the end of his webpage. If you ask him, he will give you the link where he says who is doing which one here. So, but this is a crazy project. No, so a lot of these are finite. So a lot of them are finite and a lot of them are easy to do, and they've done it in the book. So this book contains some of these. And then there are a lot of them in this room. And then there are 2 of them untouched, but one of them is okay, I think. But one is the car I was talking about. So V22 is the most challenging. I don't think anyone has put their name on it, but they're probably working on it. So step 3, compactify. Right. So, I mean, compactify with K, right? Oh, this is a good joke. I never thought about this. Compactify. Yeah. K-moduli. Yes. So good. So now this is what we did. So 8 inside these 105 are one-dimensional. And then amongst them, 6 of them belong to 87. So we basically, so theorem, it's not like that, but the theorem says the one-dimensional component of MKPS 3 that contain smooth Fanos are E1. This is silly. What we really do is so in each case, you write down your parameterization. It's always A1 or A1 minus some point that parameterizes the smooth objects. And then find possible limits and prove 1 or 2 is K polystable. Now, your example is this. But this guy is K polystable and others are strictly K semi-stable. Now, in the next few minutes, I want to show you something that, so there's a lot of computation at this stage, but by this point, you have a good guess of who you are going to check and try. So for each of these 6, we had a good guess, except one of them. And it took us exactly 1 year. And thanks to another conference, I was sitting in the room and the bingo came. So I'm going to tell you the bingo. So the crazy guy, you take P2 cubed And then in it, you take X given by 3 equations of degree 1, 1, 0, 1, 0, 1, 0, 1, 1. You write down a parameterization. You decide which ones are smooth. You find the limit. So this is, let's say, this is the P1 I'm going to find at the end. And I have 0 missing. And I have infinity missing. This one has 2 missing. And this guy, you can fill it up by a toric example. So there is a toric guide that is known to have a deformation into this. And for this guy, the barycenter is the origin. So you know by theory that this is K-polystable. Now this guy. So we wrote down several different ways of writing the parameterization. Each time you take the limit is horrible, right? Sometimes not normal, sometimes just strictly K-semi-stable. And we just we got mad. We didn't know what to do. But then the key point is just not to do this, right? So when you write down a parameterization in your space, you're basically saying my limit lives in the same space. So I'm expecting the GIT of this determines my limit, right? That's not going to work. So people who are a little bit older than me should know this is a complete intersection. So Buchsbaum, Eisenbach, that says codimension 3 Gorenstein schemes are the Pfaffian. So they're not complete intersection, but they're not so bad. They're given by, I don't know if you know this thing. So basically you have a 5 by 5 skew symmetric matrix, right? So 2, 3, 4, 1, 2, 3, 1, 2, 1. So you have polynomial entries here, and they say basically your equation, you have 5 equations that come from the 5 Pfaffians that you get here, right? And the equations are basically this times that plus this times that. And 5 of them you can write down. Not important. Important, but you don't need to know what they are. Thing is, they're not complete intersection. You have 5 of them. So what you do is, so this guy is exception. He just escaped and became complete intersection. So you write it in that format, 5 equations. Of course, 2 of them are redundant, but you write it and then take the limit. The limit is not redundant, and you have the guy. And it took us 1 day to prove his K-polystable. So 1 year to find it. So my message, GIT is not that powerful to tell you much about K stability. So it does in some peculiar cases, but not always. So you should just basically forget it. Use it as a guide, but don't take it serious. It's a good friend. Good. Thank you for listening.
Thank you. So any questions?
Excellent question. So all of this thing comes from differential geometry initially, right? So they just don't care, right? Now, so the answer is 0, right? The point is you have K stability and you have several evaluative criteria. I wrote one of them. So this delta thing. So you can think of delta as a stability condition on its own, and there are other conditions. So we know that for Fano's over complex numbers, these are equivalent. That's why we can work with them. But now you can pick any of these you like and define it in characteristic P and see if they give you the moduli. Or if they don't, that's also good too. They don't give you. But also for polarized varieties over C, don't know much. Right? So, yeah. So the answer is yes, plenty. So what I'm saying here is there are lots of questions over C to do. There are also lots of other questions in other scenarios. There was another one. Yes, someone.
The status of most challenging V22. Do you have a bound of singularity?
Smooth is challenging. Yeah. So V22. So this is 6-dimensional. You have one guy here. I'm writing only the smooth one. So there is one here with the GA action. So this is not reductive, the automorphism. Therefore, this is unstable. So not all the smooth ones are going to be K-stable. And then you have the Mukai Umamura. So this one has a PGL2 action. So this one is known that is K-stable. And then passing through it, there is a whole one-dimensional family with C star mu2 action. So these are all known to be K-polystable by Shramov, who is supposed to be here but is not, and Cheltsov. And the rest completely open. Completely open. So we know a general one should be by openness. Donaldson has a conjecture here. It tells you which ones should not be stable, K-polystable. So we expect more non-polystable ones here, but there is no proof. There is no.
Where do these embeddings come from? Like the embedding in P1 to the 5 to the 2, or this one in P2 to the 3? How do you know?
I give it another talk now. So I can give you a quick answer. So we so it started by Karstrik and Petracci doing similar things to Laurent inversion that you're talking about. So basically, so people who do mirror symmetry, you will see later, they also work with Q-Gorenstein deformations of Fanos, and we are working with Q-Gorenstein deformations of Fanos, right? So they took quartics, and then they took, conjecturally there, Q-Gorenstein deformation families up to deformation are in one-to-one correspondence with is maximally mutable Laurent polynomials divided by mutation, right? So you deform your quartic to a toric quartic that you know, and then you run your computer for, and then you write the, you run the polytope of this thing, right? You write the polytope, this is easy. And then you make your computer run more than, that's what they did, more than 100,000 mutations, and then store them. And for each of them, you construct a toric variety. And then for that toric variety, you check if it's K-stable or not. This is easy. It's just the barycenter of the anti-canonical divisor, polytope. And only 3 of them came out to be K-polystable. And those 3 live in that space. And then they showed us, and then we said, oh, you know, all of these guys should be. So.
Oh, I thought you started with a specific thing that you wanted to find.
No, it came from mirror symmetry. It was nice. It was fun.
Okay.
Yeah. Which one? Yeah.
Can you hear?
Yeah.
So you gave the example of the quartic threefolds in P4, and in the limit you have the hyperelliptics, and you alluded that the hyperelliptics are obtained by the current blow up of the GIT along
in
the double.
it's the locus of
quadric?
double quadrics.
Double quadrics. Yeah. Where do the others come from? The third case.
Yeah, it's not even a divisor here, right? It's a codimension.
Do they already appear in the current blow up, or do you need to do more?
Oh, I don't know. Or maybe it's maybe it's one of the parts of a stratification. That would be good, because then there is another one in between, right? Yeah. Thank you.
How about the modular space of parameter vector? Because they have the same variation as curve.
Yes. So I'm not super updated on this, but some work is done, and I heard from conversation that a brilliant PhD student has worked this out, that which cases that moduli is actually general type. So some work is definitely done, but it's more than that. So there are cases of even general type, the K moduli. Yeah, sure. But doing the compactification and I don't know. It's bigger probably. Yeah. But, I know some people doing it, but yeah. So some, I don't know. Yeah. So, I mean, the name you want, because it's still not published, I tell you in private. So. Yeah. Yeah, I just, he's your mathematical brother. Anyway, so yes, the answer is yes. There are some cases, yes, but not in Fano threefolds. I think Fano threefold, they should all be rational. Too much. One more, yeah.
Are there other examples of degenerations or limits that can be obtained, say, through some kind of determinantal-like description, like the one you gave for the Fathians, that don't come from the GIT limit?
I don't know, and there's one in my pocket I'm trying to prove, and it's a limit of quartics, and it's again Pfaffian. So yeah, but yes. So maybe, okay. The GIT that we see is not going to give you something, but you can think of these as some GIT on some Grassmannian. Maybe GIT always gives you, but just different GIT, right? So, yeah, thank you. Thank you. Oh yes, that's very